System F, also known as the polymorphic lambda calculus or the second-order lambda calculus, is a typed lambda calculus that differs from the simply typed lambda calculus by the introduction of a mechanism of universal quantification over types. System F thus formalizes the notion of parametric polymorphism in programming languages, and forms a theoretical basis for languages such as Haskell and ML. System F was discovered independently by logician Jean-Yves Girard and computer scientist John C. Reynolds, whereas simply typed lambda calculus has variables ranging over functions, and binders for them. System F additionally has variables ranging over types, and binders for them. As an example, the fact that the identity function can have any type of the form A would be formalized in System F as the judgment where is a type variable. The uppercase is traditionally used to denote type-level functions, as opposed to the lowercase which is used for value-level functions. As a term rewriting system, System F is strongly normalizing. However, type inference in System F is undecidable. Under the Curry-Howard isomorphism, System F corresponds to the fragment of second-order intuitionistic logic that uses only universal quantification. System F can be seen as part of the lambda cube, together with even more expressive types lambda calculi, including those with dependent types, logic and predicates. The type is defined as where is a type variable. This means is the type of all functions which take as input a type alpha and two expressions of type alpha, and produces output an expression of type alpha. The following two definitions for the Boolean values and are used, extending the definition of Church Booleans. Otherwise, if such functions could be named, then there would be no need for the lambda expressive apparatus capable of defining functions anonymously. Then, with these two terms, we can define some logic operators. As in Church encodings, there is no need for an IFTHENELSE function, as one can just use raw-typed terms as decision functions. However, if one is requested, will do. A predicate is a function which returns a typed value. The most fundamental predicate is ISZERO, which returns if and only if its argument is the Church numeral 0. System F structures. System F allows recursive constructions to be embedded in a natural manner, related to that in Martin-Löff's type theory. Abstract structures are created using constructors. These are functions typed as. Recursivity is manifested when itself appears within one of the types. If you have of these constructors, you can define the type of as. For instance, the natural numbers can be defined as an inductive data type with constructors. The System F type corresponding to this structure is. The terms of this type comprise a typed version of the Church numerals, the first few of which are 0, equals 1, equals 2, equals 3, equals. If we reverse the order of the curried arguments, then the Church numeral for is a function that takes a function f as argument and returns the th power of f. That is to say, a Church numeral is a higher-order function. It takes a single-argument function f, and returns another single-argument function. Use in programming languages. The version of System F used in this article is as an explicitly typed, or Church-style, calculus. The typing information contained in lambda terms makes type-checking straightforward. Joe Wells settled an embarrassing open problem by proving that type-checking is undecidable for a Curry-style variant of System F, that is, one that lacks explicit typing annotations. Wells' result implies that type inference for System F is impossible. A restriction of System F known as Hindley-Milner, or simply HM, does have an easy type inference algorithm and is used for many statically typed functional programming languages such as Haskell 98 and ML. Over time, as the restrictions of HM-style type systems have become apparent, Languages have steadily moved to more expressive logics for their type systems. As of 2008, GHC, a Haskell compiler, goes beyond HM, and now uses System F extended with non-syntactic type equality. For example, System F omega. While System F corresponds to the first axis of the Barandig's lambda cube, System F omega, or the higher-order polymorphic lambda calculus, combines the first axis with the second axis. It is a different, more complex system. System F omega can be defined inductively on a family of systems, where induction is based on the kinds permitted in each system, permits kinds, and where n, in the limit, we can define system to be. That is, F omega is the system which allows functions from types to types where the argument may be of any order. Note that although F omega places no restrictions on the order of the arguments in these mappings, it does restrict the universe of the arguments for these mappings. They must be types rather than values.